So problem 5 in this tutorial sheet, that probably should actually be problem 4 with the order it's out as a question sheet, but this problem is reacting hydrogen bromide with this this system here. What's our reaction mechanism? So we're told we've got a product already, and our product is drawn out in the question sheet to be as follows. So we've got the hydroxy here, got to put the aromatic ring in place, so methyl to the carbon trifluoride group. So what's our reaction mechanism here? So hydrogen bromide again is electrophilic, so we've got a delta positive and delta negative part of the hydrogen bromide molecule. So again, if we were just to consider this as a mechanism, we need to form stable carbocations. So nucleophilic lone pair of electrons from the alkene bond attacks the hydrogen bromide and you form the carbocation. Now we have a more stable carbocation here, which is the benzylic system. So let me again draw out the skeletal form of this molecule without thinking too much at the moment about putting the carbocation centre in. So this is what we've got. If we break the alkene double bond, we must form at one of these two carbons a positive charge. If we were to put the positive charge there, this would be a secondary carbocation. If the positive charge would be here, this would be a tertiary carbocation. So we've got by stability a more stable carbocation here. But the other thing, if this was to be the carbocation and this was to be reconfigured as sp3, not only is it tertiary, but it's stabilised too via resonance from the aromatic ring. So we can actually move electron density and form some resonance tautomates of this. So this is the most stable carbocation, and again the incoming bromide was to attack towards the carbocation centre, and you would form at this point this system. We'll just draw the rings out again. And then we have in the reaction we have water. So the water molecule then with reflux could be nucleophilic and attack this carbon and break the carbon to bromine bond. So we would then get this kind of system. Which would then, this product would then collapse down to the product. So let's just say if this step is repeated with reflux, we could suggest that this is a nucleophilic substitution of the water molecule again back towards the antibonding orbital of the carbon here, SN2 chemistry. But this system here, because it's stable as a form as a benzylic system, there's nothing to suggest that if you were to take this and heat it at reflux with water as a solvent or as a nucleophile, that you shouldn't remove the carbon to bromine bond in an SN1 step. So you go back towards this carbocation, this benzylic system, where the water molecule then can actually move its electrons towards this carbocation. We're not being asked at this point what our views are as this SN1 or SN2, but I suspect that if you were to take this system and heat it via reflux with water as a solvent, it probably moves more via SN1 chemistry, so the carbon to bromine bond breaks to reform this intermediate, this carbocation, and then water attacks that. Now, in all of this tutorial sheet at the moment, I've not given you many examples of orbital overlap. So for the last question here, if we just look at this again as a reaction system, and we look at orbitals, so let's draw this ring system out again as follows. So we'll make sure this is the aromatic ring, CSV file to CF3, and I've just kind of discovered straight away that I've drawn this incorrectly, which is very good. So what I will do, I'll make this the p orbitals, I'll put that in, and I've no eraser in my office, so we'll say this is carbon 1, 2, that's the NH, put it that way. So this here isn't the double bond, this is the double bond. I'll take another pen and I'll try and etch this out or colour it out with maybe this green pen so we can get rid of that so it's not the double bond character. So here's our system. If we react to hydrogen bromide, well, the hydrogen is a 1s orbital and the bromine is p orbital overlap. So we'll put bromine in like this with a p orbital overlap. That's the p orbital, and then the lone pair of electrons in this shape. So we've got this hydrogen to bromine bond with an s orbital overlap with the p orbital of the bromine. But you can consider as well that the hydrogen might have this supposed antibonding orbital as well, this 1s antibonding orbital. That's 1s sigma. So when we attack here as a nucleophile, it's actually this orbital overlap with the p character of the double bond which overlaps with this 1s antibonding orbital. So in a new sense here, I'll draw this carefully as we go along. Carbocation is supported possibly on either that carbon or that carbon, so we're going to go back and say, well, this is the most stable carbocation, so the carbocation should go there. And we then have the rehybridization of this carbon back to sp3, so we have the original carbon to hydrogen bond, so we'll put the hydrogen here as an sp3 orbital, and this carbon to hydrogen bond, so this is the hydrogen now from the HBr. So we then support this benzylic system here where you have incoming water molecules, again moving the lone pair of electrons towards the vacant p orbital via orbital overlap. So this again is kind of showing this reaction mechanism where when we talk about an alkene reacting with an electrophile, the alkene p character is nucleophilic towards the antibonding orbital of the hydrogen. So this is the kind of mechanism as an overlap of orbital states. Just to recap, what's our major products? Well, as shown in the schematic, that's our major product. We suspect again electrophilic addition of the HBr. We form the benzylic carbocation by stability, nucleophilic attack of bromine to give this species, and then maybe some reflux with water, possibly back SN1 chemistry to form this intermediate carbocation, or SN2 chemistry to attack the antibonding orbital of the carbon here by the nucleophilic attack of water to give our product. Okay, so with that in mind, I've just actually said this is a water molecule attacking. I should clear that up and say, obviously, from a mechanism, this isn't water, this will be a bromine species. So this is not water, this is a bromine or a bromide anion that's attacking at that point. Okay, so anyway, live tutorials as you go along. I'm not going to reorganise this and re-edit it, but not a water molecule at this point, of bromide ion. My mistakes, and my apologies for my mistake. Thank you.